In this example, we're actually going to do a couple of examples related to solving systems of multiple reactions in an isothermal CSTR. So the problem statement reads, the following reactions are taking place in the liquid phase in a CSTR. We're given three reactions, reactions 1, 2, 3, and we're given rates for each of those reactions. Note that reaction 1 is written in terms of species A, the rate of reaction 2 is written in terms of species D, and the rate of reaction 3 is written in terms of species E. This will become important in a minute. We're given information about this system of reactions. The entering volumetric flow rate we're given, and we're given the entering concentration of A. In the first example, we're going to consider the case where the CSTR operates at concentrations of A, B, C, and D that are given. It's also operating at some concentration of E, but we don't know that, we're not given. Okay, so the first question asks us to determine the CSTR volume. So we get the CSTR volume by writing an equation, and that equation is going to be the mole balance. Here we have 5 species, and in fact we can use the mole balance of any of them to solve for the volume. So in this example, we have one unknown, that's volume, and so we only need one equation. So we can pick any mole balance. So let's pick one that's easy. At first glance, species E might be a good choice. So if we go back and look, because it's only involved in one reaction. However, we don't have any information on species E, so we're not given its concentration. So if we write the mole balance for species E, then we have 2 unknowns, the concentration of E in the reactor and the volume, so that's too many. So we're not going to use that one. We'll say we are not given its concentration. So it's mole balance alone. Doesn't give us enough information. So we could couple the mole balance of species E with some other mole balance or a mole balance of another species, but why do that? Why not just pick a species for which we have information and use that to solve for volume? Looking at the species again, species B only involved in one reaction, so it's going to be a good choice. It is not necessary that the species be involved in just one reaction. It just makes our lives a little bit simpler because when we go to write a net rate for that species, we only need to consider the rate of the species in one reaction. So we don't need to even construct a stoichiometry matrix for this problem. If we have this scenario, we can simply write just one rate based on the reaction that the species is in. Now we're not always going to get this lucky, but I just want to show this example of a problem where we could solve for a lot of different information, but we can also isolate smaller pieces to solve for separately. Okay, so let's do this then. So writing, if we want to write the mole balance of species B, we're going to need the net rate of species B. So let's get that, and then let's insert that into the mole balance. So net rate of species B is going to be the rate in reaction 1, because that is where species B is involved. It's not involved in any other reactions. If we go back and look, reaction 1, reaction 1, the rate is given to us with respect to species A. So we're going to need to adjust a little bit, and we can use the net rate or the relative rates equation to do this. If you recall, that's going to be, you can write the rate of any species divided by its stoichiometric coefficient equal to the rate of another species divided by its stoichiometric coefficient, where stoichiometric coefficients for products are positive and for reactants are negative. Translating this to this reaction, we would say R1B over 1, so B is a product in this reaction 1, so it has a positive stoichiometric coefficient, is going to be equal to R1A over minus 3. A is a reactant, so it has a negative stoichiometric coefficient. In that case, then, R1B is going to be equal to minus 1/3 R1A. We know what R1A is. We're given that. So this is, I can further substitute in. This is going to be 1/3 times K1A times CA. And I know what both K1A and CA are. So K1A is going to be 7 per minute. I'm given that information. And CA is going to be 0.10 moles per liter. And I'm also given that information in the problem statement. Now I can take this information and put this into the mole balance. So we know what the mole balance is for a CSTR. That's going to be V is equal to the flow rate coming in minus the flow rate coming out. Notice that I'm using flow rates and not conversion. Conversion is not a helpful variable here. The conversion of the B, in this case, I'm solving for B, which is a product. So how do I even define its conversion? If I was trying to solve, for example, for A, which is a primary reactant in this system of equations, A is involved in multiple reactions, so conversion doesn't tell me the partitioning of A going to one reaction over another. So conversion doesn't give us enough information. So when I solve multiple reactions problems, I'm going to use the general form of the mole balance in terms of molar flow rates rather than the simplified version in terms of conversion. Okay, so anyways, getting back to that, I'm going to, the term on the bottom here is going to be this RB net. In this equation, I know that F B naught is equal to 0. The only thing coming in here is A, so the flow rate of B coming in is 0. And coming out, I don't know the flow rate, but I can easily solve for it. That's going to be the concentration coming out, which I know, and I'm going to multiply that by the volumetric flow rate. This is a liquid system, so the volumetric flow rate is constant, and so I can use the inlet volumetric flow rate. So this value is going to be 100 liters per minute, and I'm given this information of being 0.93 moles per liter. So now I can enter all of this information into the mole balance and solve it. And if I do all that, I get an answer of 399 liters.